Hi everyone, I'm Joon, and this is a joint work with Vitercik from Singapore and Kandasamy using this audience. So what is the problem I want to solve? We want to solve is a targeted marketing problem. And the targeted marketing problem is made of two things: target and marketing. And first, let's consider what is the marketing problem. So I want to sell a new whisk phone and to some market. Let's consider just single market. Obviously, there is a sales goes down as price goes up. This is a demand, and the profit doesn't look like a demand, but it may have peak, and it goes below the zero because the profit is defined as revenue minus cost, and we're assuming that the cost is fixed. And then we want to find the optimal price, and that's the whole story for the profit maximization. But what happens if we change the cost of advertisement? So if we spend more money to the market, that will shift the demand of the curve. It's called advertisement elasticity. And the spending more will change the profit curve too. So therefore, we have to choose new optimal price. So in this case, the optimal price will be slightly higher, and it will give a little bit more profit. And mathematically, let's say the sales for B and the price is for P, then we want to maximize this function P of E minus C. And the C star P star is the maximum price and the optimal price and the cost. In the target market problem, we have multiple market, let's say United States, and there are many places. And it's called the media markets. So we have different sectional broadcasting networks. So each network is each block is considered as one market, essentially, because they don't share the broadcasting network. And let's say just pick two places, Madison and New Haven, and there are two demand curves. Even though they look similar, but they're slightly different as well. And one profit curve. So profit is summed over all these different markets. And as usual, as before, if you change the marketing cost, advertisement cost, this will shift demand. But here the shift is independent, and we're choosing different variables of advertisement cost for different each market. So in this case, the Madison shifts a little bit, and New Haven shifts a little bit further. If we choose some marketing cost variables, and then the profit is maximized at new price. Mathematically, we have this expression. There's a common price P, and the demand curve for each market, and the CI is for marketing cost in each market. And we want to maximize the optimal this profit. We want to maximize the profit by choosing the optimal advertising cost for New Madison, the optimal advertisement cost for New Haven, and the common price, which should have started. And now the problem that I described was offline setting, and we want to make it more exciting to solve, and that gives this formulation of Bandit Profit-Maximization for targeted marketing. At each round, the seller decides the advertisement expenditure for each market. And let's say there are n markets, and the common price, P. And then after the round, the seller observes the number of sales in each market, which is a function of PPI and PP. And this is this index goes over I equal to 1 to n. So that means the seller observes sales in each market, and here, this function is evaluated at these specific points. So therefore, it's a bandit feedback. You don't observe anything about this function. So you only observe the function value evaluated at these points. And we assume these demand curves can shift over time, but in oblivious way. That means demand curves can change over time due to some seasonal effect, economic cycles, competitions, but do not depend on sellers' previous choices of prices and marketing costs. So we're looking at the macroscopic changes of demand curves. And one different thing here is that we actually Where's the cursor? Yeah. So we are looking at choosing a single price for one commodity, and the common pricing is needed for preventing arbitrages. For example, you can buy from the same good from the cheaper market and sell it at a higher price at different market, or also you can guarantee some fairness between these markets. So this is the problem setting. And then we want to minimize the regret, which is defined as the profit earned by the algorithm, which is the gross profit, and the profit achievable by the best fixed decision variables. That means best fixed, yeah, costs and prices.
The D function itself does not change across the time. I mean, the functional relationship between D and other arguments C and P.
It will change. So D has actually an index of T, DTI. So you point. Oh, I have to point here.
Okay, so the relationship between demands and the campaign costs does change.
Yeah, yeah. So DTI, so T depends. So there's one index like T. So T goes to 1 to T. So that function DTI changes over time. And we want to impose some assumptions on these functions. And the first assumption, so we have two assumptions, which is separate, is that this function is monotonic over P and C. So if you have a larger price, they will decrease. Having a more, if you invest in more on the advertisement, it will increase. And the second assumption, second case we're looking at is when everything is same, but the cost is response with respect to the marketing is concave. And there's an economic interpretation of this. This exactly is the diminishing returns for marketing. And so let's first summarize our research. So prior works, just as like a climate bulletin paper, the optimization goal is over a single demand curve, and the goal is to maximize the revenue. And in this work, we want to optimize profit over multiple demand curves over different markets. The regret bounds from the climate bulletin paper is height, near height, T to the 2/3. And in our case, we have, for monotonic case, we have near height upper and lower bound, which depends on the N and T, and it is N to the T to the 3/4. And the cost concave case, interestingly, it also have T to the 2/3, which is the same as the climate bulletin paper. So we can solve this problem without causing more inefficiency. So the key technical challenge of solving this problem, when I talked about this project to someone else, and he told me that is there something special other than discretization plus EX'24, or just discretization plus any multi-channel bandit problem, bandit algorithms. So this is a very I would say a natural approach to solve this problem. But if you use any off-the-shelf multi-channel bandit algorithms, then you will get the regret, which depends on like a square root of KT, where K is the number of arms, or in our case, K is the number of discretizations. So in our case, let's compute the K, then it will be the K with the size of discretization times the size of post discretization to the power of the number of markets. So you can optimize the size of discretization to make it sublinear, but it will depend, the exponent will depend on the number of markets, which is not optimal, far from optimal and very inefficient. And this is because the number of markets sits in the exponent. Then the second issue is that we set the common price couples different markets. And otherwise, if the markets have different prices, then you could use just the EX'24 algorithm. But in our case, for example, marketing cost for market 1 and the marketing problem for market 2 is coupled by the common price PT, and that gives some problem. So again, the common pricing is needed for arbitrage fairness and fairness. So we want to design an algorithm that decouples pricing and marketing. So first idea is to have this mental model of the algorithm, So let's say the algorithm have many components and one price setter and n local marketers. So it's like a distributed algorithm in this picture. So the price setter samples the price first. So and then broadcast this price to local marketers, and the marketers adjust their advertisement cost by sampling from their own distribution given this PT, which is broadcasted by the price setter. And then they apply these decision variables, CT1, CT, and the PT to market. And then they get the feedbacks. So after the round, each marketer gets the feedback from the market, which is the number. And then the marketer sends this information to price setter. And then they will update their strategies using these numbers. Okay. So this is the general view of the algorithm, and more specifically how to update these strategies. And to figure that out, we can just figure it actually. We can go over like a backward induction and then figure that what should be the right choice of the loss. But after that, you will get some interpretation of this loss. So to explain these strategies, let LTI be negative normalized local profit, and we update QT naught and the QT1 to QTN using exponential weights or multiplicative weight method. And there exists, so then each one is updated by different loss functions. And this is how a loss function looks like. And I'll explain more about it later in this slide. So basically, these losses look very close to the losses for the EXP3, but there are some components that are not the same. So first of all, it is divided by QTI and QT naught. So it is the inverse probability weight. So that we can, if you take an expectation, then this will cancel out, and it will give you an unbiased estimator of LTI. But there's also small parameter that prevents us from making it unbiased, which is gamma. So it introduces a small bias, but it is essential to control variance from the other loss function. So this looks like the IPW estimator from X3, but it contains the extra factor of QT naught P plus gamma inverse, and that gamma is very important. And for price setters loss, so F was the loss for each marketers, and the H is loss for the price setter. It comes with average loss. So their goal is the price setter's goal is to minimize the average loss. And there's a term that looks similar to the QT naught P T plus gamma, exactly the same, but yeah, it is also inverse probability weight with some gamma, and this gamma this gamma is if you remember from other literatures, it is often called implicit explorations, and the other term is called exploration bonus, because if you look at these terms, if you work out the math correctly, then these terms actually represent you're encouraging more explorations, because it discounts less for the price unexplored. And the intuition is that don't exploit the best price too early, because we have many local marketers to work on, and these local marketers need time to optimize their marketing variables. So do not jump over the price too early. So that's the key takeaway. And for cost concave case, since our algorithm is modular and it works in the black box, a little bit of black box way, so we can actually replace the EXP3 type components with the kernelized exponential weights by Gubeck et al. And then we can get through the almost same mess that we can get the regular bound of 2 to the 3. Okay. And again, this is identical to that of the price only revenue maximization problem. And then finally, we're going to talk about some low bound. There's a sequence of monotonic curves, and our low bound is n to the 3 to the 4th times t to the 3 to the 4th, which is slightly weaker than n to the t to the 3 to the 4th. And this is a proof sketch, a little just sketch of this hard instances. And the instance, the baseline instance, so it looks like this, which is for the second picture, it's actually exactly the same thing as you can get from the reliability paper. But for the first one, it is slightly different. So because these instances are two-dimensional, and in this case, optimum prop is 0, and we can implement the best price and the cost by just shifting these steps a little bit, and the optimum prop will be the order of epsilon. So using the similar standard techniques, you can get the lower bound of t to the 3 to the 4th and expand that to the n to the t to the 3 to the 4th by copying these instances n times and couple them in a certain way. So summary, we propose the near optimal and also optimal bandit algorithms for targeted marketing problem with respect to monotonic and post-concave demands. Especially for post-concave demands, rigorous scales as n to the t to 2 to the 3rd, which is optimal even when there's no post-concave. And two open problems. Can we close the rigorous lower bound and upper bound gap in the monotonic demand case? And what if there are non-trivial correlations between markets? So in our case, we assume that there is no correlations between these markets. They respond to their own marketing variable, but it could possibly they could have some correlations, and how to deal with that, that is the next question. Thank you.